All right, let's get to it. The first thing we'll talk about in section 4.3 is the standard algorithm for multiplying fractions. And we've seen this already, but just as a reminder, if we wanted to multiply 3/4 times 2/3, we don't need a common denominator for multiplication. We just multiply numerators. 3 times 2 is 6. Multiply denominators. 4 times 3 is 12. And so 6/12 would be a reasonable answer here. We could reduce that if we were so inclined, if we wanted to reduce that, or if we were told, write all your answers in lowest possible terms, then we'd need to reduce it. Those are both even numbers, so you could reduce that way, or you might look at that right away and see, well, 6 will go into both of those, so I can just reduce that. 6 will go into 6 once, 6 will go into 12 twice, so really that's just 1/2. That's our standard algorithm for multiplication of fractions and how to reduce them. Next, I want to look at using the area model for multiplication. The area model is where we kind of draw a big shape, usually a rectangle or a circle, to represent 1. So there's our rectangle representing 1. And here, the problem I want to work on is I want to multiply 3/4 times 2/3. Here's how we're going to go about that. I need to cut this rectangle up. What I'm looking for here really is the multiplication is a word we can substitute for that is of. What we're looking for here is 3/4 of 2/3. We're multiplying 3/4 times 2/3. One thing I want to do is I want to cut my rectangle into thirds. So you can do it in either direction, but I'm going to cut my model into thirds that way. And now I want to indicate 2/3. So I'm going to shade 2 of those 3/3. And I'll just do the 2 at the bottom. You can do the 2 at the top. It doesn't matter either way. And so the first thing I want to make sure we're good with is that picture I have right there represents 2/3. We have a whole, and we chopped it into thirds and shaded 2 of them. That's 2/3 with the area model. If there's any confusion or uncertainty about that, let me know. Awesome. Now what I want to do in order to multiply these is I'm looking for 3/4 of this 2/3. So what I'm going to do is I'm going to cut the rectangle into fourths the other way. So I've cut it into fourths, and now because what I'm interested in here is 3/4, I'm going to shade 3 of those. It could be any of them, but I'll go ahead and go this direction. And so what I've done is I shaded 2/3 and I shaded 3/4. And you might be thinking, how in the heck is this multiplying those two fractions? Well, what I want you to notice here is this. Where the overlap is, the boxes that have shading both directions, both colors, are these right here. You know what? I'm going to do it individual boxes. These are the ones where 3/4 and 2/3 overlap. And what you'll notice is that that's 1, 2, 3, 4, 5, 6 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 out of 12 boxes are shaded. And as we saw just a minute ago, when we multiply 3/4 times 2/3, we get 6/12, which we could reduce to 1/2. One thing I'll say about this area model for multiplication is when you're working with kids, it's great to give them the opportunity to discover something rather than just telling them. And so if you were to give them the problem 3/4 times 2/3 and start by doing it this way, let's find 3/4 of 2/3. We're going to shade 2/3. We're going to shade 3/4 of that. What did we end up with? we ended up with this answer of 6/12. And then you kind of give them a chance to say, what could we do to get from here to here without having to draw a picture? And your fingers crossed, maybe somebody in the room recognizes, hey, wait a minute, 3 times 2 is 6 and 4 times 3 is 12. And we could just multiply numerators, multiply denominators. And you've given them a chance to discover it on their own. This is also sort of a visual representation of what's happening when we do multiply those fractions. I think it's really cool. I think it's really valuable. And I want to make sure to share it with you for that reason. I want to give you a chance to practice one using the area model for multiplication. I want you to try multiplying 3/5 times 1/2 using the area model. I won't really set up a poll for this because it would just, be what the correct answer is, but I want you to try to draw this one and do it with the area model. I'm going to start working on this. I'm not going to rush my way through it. And if you have trouble or if you have questions or you're not sure why something went a certain way, you let me know. We start out with one whole thing, which a rectangle is usually a pretty good choice. I want 3/5 times 1/2 or 3/5 of 1/2. So the first thing I'm going to do is cut this in half. You don't have to cut it any of the certain directions. You could cut it either way. Maybe you cut yours horizontally. That's okay. And then so I want to shade 1/2. So there's half of my rectangle. And now what I want to do is 3/5 of that. So the other way, I've got to cut it into fifths. Now, cutting it into nice, even, perfect fifths is really hard to do. They don't have to be perfect. They just have to be fifths. And then I want to shade 3 of those fifths. So we'll do that. And then what I end up with as being shaded by both colors, both directions, is I have 1, 2, 3 of the pieces are shaded out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so 3/10 would be my result, multiplying this with the area model. And we can kind of see that 3/5 times 1/2 is certainly going to be 3/10. Let me know if you have questions or if you had any trouble with that, but that's using the area model for multiplication. Okay, a little bit more about division. What is division anyway? What is it asking us? If we are given the question 12 divided by 6, and let's face it, we can all get to the fact that 12 divided by 6 is going to be 2. That's fine. We can answer the question, but what is it we were really being asked? What we are really being asked there is, how many 6s does it take to make 12? Well, right. How many of these does it take to make this? How many 6s does it take to make 12? And our answer, of course, is 2. I want you to keep that in mind as we look at some other division problems going forward. What this question said was, how many 6s does it take to make 12? Hold on to that idea. Something else I want to address with you down here at the bottom of the page is the idea that division is the same as multiplying by the reciprocal. First, we have to make sure we know what reciprocal is. If we had the number 6, what is the reciprocal of 6? That would be the opposite, but definitely a good guess. -6 would be the opposite, and that's an important word too. Opposite's a very important word. Reciprocal is an important word. What's the reciprocal of 6? A little bit ago, when we first started looking at multiplying fractions, we could say, well, if we put it on the bottom of the fraction, if we flip it over, if we were to write 6 as a fraction, it would be 6 over 1. The reciprocal is what we get when we flip that upside down. When we flip it, we get the reciprocal of 6, which is 1/6. So the reciprocal is, if we were to write that number as a fraction, flip it over. So let me just ask you a really quick question. I expect all of you to get it right, but I just want to make sure you're with me on this. What is the reciprocal of 2/3? Good Zoshel, good Leslie, good Stephanie, good Emily. Yes, 3/2. If you aren't sure about that, you're confused about that, let me know. All we're doing is flipping it over, and that's how we get the reciprocal. Which brings us here that division is the same as multiplying by the reciprocal. So if I have 12 divided by 6, instead of division, if I want to make this a multiplication problem, I can, because division is the same as multiplying by the reciprocal. So instead of 12 divided by 6, I can change this and make it 12 times the reciprocal of 6, which is 1/6. These two things are exactly the same as each other because division is the same as multiplying by the reciprocal. If we go ahead and do that multiplication, we can see what happens. 12 over 1. Oh, okay. Very important. All right. So division by 6 is the same as multiplying by the reciprocal of 6. We do not want to take the reciprocal of that first number. We only want to take the number of the second number. So dividing by 6 is the same as multiplying by the reciprocal of 6. We do not want to take the reciprocal of 12. 12 is the thing that we're chopping up. And we're going to, how many 6s does it take to make 12? 12 we're leaving alone. It's the 6 that we're going to take the reciprocal of. So I'm glad y'all brought that up. Perfect point. So dividing by 6 is the same as multiplying by 1/6. But the 12, we're going to leave that alone. Correct. 6 over 1 and 6 are exactly the same as each other. The reciprocal of 6 is what we get when we turn that upside down. So anytime we want to take a whole number and write it as a fraction, we just need to put a 1 in the denominator. You know, if we have 9 and we want to write it as a fraction, it's 9 over 1. If we have 12 and we want to write it as a fraction, it's 12 over 1. And down here at the bottom, if I want to multiply these, I need that 12 to be written as a fraction. So I'll write it as 12 over 1. And now I can multiply, because I know the rule for multiplying fractions. To multiply fractions, I just multiply numerators, that's 12 on top, multiply denominators, that's 6 on the bottom. And what you'll see here is when I multiply those, 12 times 1 is 12, 1 times 6 is 6. I get 12 over 6, which this fraction tells us to divide those, and 12 divided by 6, sure enough, is 2. When we first started on this page, we said, what's 12 divided by 6? And we're all very comfortable with the idea that that's 2. And we did a little work over here to get to division is the same as multiplying by the reciprocal. Well, let's test that out and see if it worked. When we took 12 divided by 6 and rewrote it as 12 times 1/6, because division is the same as multiplying by the reciprocal, we get 12 divided by 6, which is 2. We get the same answer. For right now, you might be thinking, What the heck? That's an awful lot of trouble. Why would I rewrite this as 12 times 1/6 when I could just do 12 divided by 6? That's a fair question, and I'll show you in the next one. What if we wanted to do 3 divided by 1/4? Now I want to do 3 divided by 1/4. Off of the top of my head, how many, 12 divided by 6, okay, I can do that in my head, but 3 divided by 1/4, that's a whole different thing now. Let's look at this a few different ways. The first thing here, the question is, how many 1/4 does it take to make 3? That's what this question is. In the same way that this is, how many 6s does it take to make 12? This question is, how many 1/4 does it take to make 3? One way you could do this is with the area model. You could say, you know what? Here's 3. How many 1/4 does it take to make 3? Well, I'll chop these into fourths. And now I'm going to figure out how many fourths did it take to make 3. It took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many 1/4 does it take to make 3? It takes 12 of them. So 3 divided by 1/4 is 12. First, I want to make sure we're okay with that. How many 1/4 does it take to make 3? How many 1/4 would you need to get 3? Something we're going to be looking at a little later on today. You know, if you had 1/4 of a cup, how many of those would it take to make 3 cups? It would take 12 of them. So, you know, baking is a perfect example of this one. It would take 12 1/4 to make 3. So let's revisit that idea that division is the same as multiplying by the reciprocal. In this one, what I want to do is 3 divided by 1/4. First question I'm going to ask you is, what is the reciprocal of 1/4? Courtney, Leslie, Zochel, you're all right. 4 or 4/1. Either way is just fine. If we want the reciprocal, we're going to flip it over. And so the reciprocal of 1/4 would be 4/1, which you could just call 4. That would be just fine. So down here, division is the same as multiplying by the reciprocal. So instead of dividing by 1/4, what we're going to do instead is we're going to multiply by 4/1. So we're going to change this problem, and we're going to change it to 3 multiplied by 4/1, or just 4. That's fine, Courtney. And so what I've got now is I want to multiply these. I'd like to rewrite 3 as a fraction. That's just 3/1. And now I multiply, and I get 3 times 4 is 12. 1 times 1 is 1, and 12 divided by 1 is just 12. Sure enough, we got the same answer we got when we drew a picture of this with the area model. How many 1/4 does it take to make 3? It takes 12 of them. This division problem, 3 divided by 1/4, gave us an answer of 12. Anytime we see division involving fractions, we are going to use this fact right here to change our division problem into a multiplication problem, and then we can use the algorithm for multiplication. Tucked in down here at the bottom of this page, I have a true or false question. Keeping in mind the problem we just did that was 3 divided by 1/4 equals 12, with that in mind, my question to you, and I'm going to throw a poll out there for this one, true or false, division always makes a number smaller. So true or false, division always makes a number smaller. We'll go another 15 seconds on this. Let's see what we've got. Okay, more false than true, but split a little on this one. All right. Couple of things I want to mention. Anytime you have a true false question, what you want to try to do is, can I find a counterexample? If I can find a counterexample, I can say it's false. Somebody who says it's always sunny in Las Vegas, you could say, no, that's not true. On March 11th, it was raining. So that statement's false. You only need one counterexample to say something's false. Now this question, division always makes a number smaller. If I have 20 divided by 5, my answer is 4. Sure enough, the number got smaller. I started with 20, now I have 4. If I have 20 divided by 4 and I divide that, my answer is 5. Sure enough, the 20 got smaller. But the problem we just did, I started with 3, I divided it by 1/4, and my answer was 12. It is possible to do a division problem and end up with an answer that's bigger than the number you started with. So division always makes a number smaller. That would be false. And right here is my counterexample. I started with 3. I did a division problem, and I ended up with a number bigger than 3 as an answer. All right, a little more about division. We're going to look at mixed numbers. This is a multiplication problem first, so let's start there. Here I have 2 3/7 multiplied by 4 1/2. When we worked with mixed numbers before, we could kind of do something with the whole number part and then do something with the fraction part. With addition and subtraction, that was okay, but with multiplication, it's not. With multiplication of mixed numbers, the first thing we're going to do is change these into improper fractions. Step 1, make them improper fractions. So we'll do that. And let's see, 7 times 2 is 14 plus 3, that's 17/7. 2 times 4 is 8 plus 1, that's 9/2. And now I can multiply these. 17 times 9, I don't know what that is, 153. 7 times 2 is 14 on the bottom. In most cases, in a lot of cases, an improper fraction is perfectly fine to write down as an answer. But since we started with mixed numbers here, I think we should finish with a mixed number. So let's go ahead and convert this to a mixed number. We'll do 14 divided into 153 and get 10 point something, something, something. All that gives me is that 10 is going to be my whole number part of the fraction I end up with. I have to figure out what's left over. And to figure out what's left over, well, 14 times 10 would be 140. So that leaves me with 13/14. So to convert 153/14 into a mixed number, the first thing we did was 153 divided by 14. Basically, how many 14s will go in evenly? And we got 10 point something. The something isn't important to us. What is important is, okay, so far I have 10 14s. That's 140. How much do I have left to get to 153? We'll just subtract. And that's where the 13 came from. And so what we wind up with rewriting this as a mixed number is 10 and 13/14. The key here is if I want to multiply those mixed numbers, the first thing we do is convert to improper fractions. I want to have you try one. I want you to divide those two mixed numbers. I'm going to set up a poll for this one, and I'm going to kind of give you a push in the right direction. If we want to divide those two mixed numbers, we need to convert them to improper fractions. Then we need to remember, division is the same as multiplying by the reciprocal. And then we're going to multiply them. So go ahead and divide these two mixed numbers. Using that process. First convert them to improper fractions, and then division is the same as multiplying by the reciprocal. Oops, I see I have a typo in there. That third one is supposed to be 2 1/3. So keep that in mind as you're looking at these. That third answer should be 2 1/3. So a couple of steps. Convert to improper fractions. Division is the same as multiplying by the reciprocal. And then at the end, you want to go back to the form of a mixed number or whole number. I'll give you a little more time on this one. Let's go 30 more seconds, and then we'll look at it together. Okay, that's an interesting result. Most of the answers are 2 26/27, but not as confident of a response as I was expecting here. So let's take a look at this one together. So with these mixed numbers, the first thing we'll want to do is convert them to improper fractions. So what we have is 6 2/3 divided by 2 1/4. Converting those to improper fractions, we'll have 3. 3 times 6 is 18, plus 2 is 20/3. And 4 times 2 is 8, plus 1 is 9/4. So 20/3 divided by 9/4 isn't really something we can do. So we have to use the idea that division is the same as multiplying by the reciprocal. So instead of dividing by 9/4, we're going to say that this is 20/3 multiplied by 4/9. Let me know if you see something that doesn't make sense. Now we can multiply numerators. 4 times 20 is 80. Multiply denominators. 3 times 9 is 27. And we have 80/27ths, which for most things would be a perfectly fine answer. But we started with mixed numbers, so let's finish with mixed numbers. To figure out how to rewrite 80/27 as a mixed number, the first thing we're going to do is 80 divided by 27. And that's 2 point something. The decimal part really doesn't matter. So we're going to have 2 as our whole number. What's happened here is we have 2 of these 27s. Now we got to figure out how much is left. Well, 2 times 27 would be 54. I'm supposed to get to 80, so I need to do 80 minus 54, and that's 26. So what I have is 2, and I have 26 more 27s. Remember what a mixed number means, right? What I have here is the 2 is 27 27s, and 27 more 27s. That's the 2 part. And then 26 more 27s. And adding all this together, that's my 80/27ths. And we rewrite it as 2 and 26/27ths. If you have questions about that, please don't hesitate to ask them. All right, outstanding. A little bit of problem solving. We'll do quite a bit of problem solving today. A tree is 2/5 as tall as a house. The tree is 9 feet tall. How tall is the house? So we'd like to write an equation here and be able to solve this. So let's just take this equation, take this sentence at face value. The tree is 2/5 as tall as the house. So the height of the tree is 2/5 of the height of the house. It's not that common for us to use capital letters as variables, so maybe I'll do lowercase here. I just want to emphasize what we're saying here is the tree is 2/5 of the house. So it's 2/5 as tall as the house, and we've got our equation set up. We just need to plug in what we know and solve. The tree is 9 feet tall, so we can put a 9 where the tree is. Then that's 2/5 times h. I want to get that 2/5 to go away. What do I want to multiply by on the right-hand side to make 2/5 go away? So I want to multiply by something on the right-hand side that'll get the 5 to cancel, that will also get the 2 to cancel. So what do I want to multiply by to make that go away? We've got 5 halves in there. Oh, what do we want to multiply by? Because if I want to solve this equation, I'm trying to get h by itself, which means I need to get rid of 2/5. So what do I need to multiply by to make 2/5 go away? If I'm trying to get h by itself, I've got to get this 2/5 to go away. What do I want to multiply by? And Nicole's exactly right. We want to multiply by 5/2. Very important word from today. We're multiplying by the reciprocal of 2/5 because that'll get the 5's to cancel and it'll get the 2 to cancel. If I multiply by 5/2 on the right, these cancel and all I have left is h. That's what I was trying to do to solve this equation. Of course, if I multiply by 5/2 on the right, I also have to multiply by 5/2 on the left. Now we'll do 5/2 times 9 over 1. 5 times 9, that'll be 45 over 2 times 1, which is 2. 45/2. Nobody would really describe a house being 45/2 feet tall. So we'll go ahead and divide that, 45 divided by 2, and we'll say that that house is 22.5 feet tall. So we wrote our equation there based on the information we were given. A tree is 2/5 as tall as the house, meaning the height of the tree is 2/5 of the height of the house. Now we have the fact that the tree is 9 feet tall. We can plug that in, and now we have an equation we can solve. That equation was 9 equals 2/5 times h. To get that h by itself, we just needed to multiply by the reciprocal of 2/5 on both sides. These cancel, and when we did that, we got 45/2, which we converted to a decimal because that would make more sense for this situation. So the house is 22.5 feet tall. If there are any questions about what we did there, let me know. Otherwise, I want to talk a little bit more about multiplying by 2/5. In the last problem we did, we multiplied by 2/5. I want to ask you a question. What series of steps would give us the same result as multiplying by 2/5? I'm going to give you some choices and set up a poll. So I want you to make sure you understand the question I'm asking here. So I'm not asking what did we do to solve the problem in the last that we were working on. What I'm asking is, let's say you wanted to multiply something by 2/5. What could, if you were going to break that down, what could you do instead that would give you the exact same result as multiplying by 2/5? What would be the exact same thing as multiplying by 2/5? One way to do this is you could try it with numbers. And actually, when we go to kind of discuss this one a little bit, I'm going to use a number. Essentially, what's being asked here is, what are the steps that are given if you are told, hey, multiply by 2/5? What does that even mean? What does that do? So, what's accomplished when you multiply by something by 2/5? We'll go another 20 seconds, and then we'll do this one together. Or we'll investigate this one together, I guess. It's a little bit of a strange question. I'll admit that. So let's see what our responses look like on this one. Okay, kind of consensus agreement on multiply by 2, divide by 6, but we're definitely spread around with the other answers. So let's take a look at this for a minute. So what we're saying is we multiplied by 2/5. What would be this? What would get the same job done? And what I'm going to do to investigate this is I'm going to go ahead and put a number in there. I'm going to say, okay, let's start with the number 10. If I multiply this by 2/5, what I would get is, let's see, 10 times 2 is 20 over 5, that's 4. So whichever answer you pick over there, when we put 10 in, we better get 4 out. So let's take a look and see. The first choice was multiply by 5 and divide by 2. So if I take 10 and I multiply it by 5, and then I divide by 2, nope, that didn't work. Multiply by 5 and divide by 2, that's not what's happening here. Okay, the second choice was multiply by 2 and divide by 5. So if I take 10 and I multiply by 2, I get 20. I divide by 5, I get 4. Hey, that looks pretty good. And you know, if you look at what we did over here, the first thing we did was multiply by 2, and then after that, we divided by 5. So the answer that most people chose was the correct one. That's good news. Multiplying by 2/5 is really, in effect, multiply by 2 and then divide by 5. Those are the steps involved in multiplying by 2/5. Just to sort of polish this one off, if I were to take 10 and multiply it by 5/2, well, let's see, I would get 50 over 2, which is 25, and that's not what we were after because we needed our answer to be 4. So that's no good. Now, in the last problem we did, in solving that equation, we multiplied by 5/2, but that was to get the 2/5 to go away. That didn't have anything to do with actually multiplying by 2/5. That was to make it go away. And then our last one down here at the bottom is divide by 2, divide by 5. If I take 10 and I divide that by 2, and then I divide that by 5, I get 1. Nope, needed my answer to be 4 for this to be correct. So out of those 4 choices, only one of them was the correct one, and it was multiply by 2, divide by 5, because that's what happens when we multiply by 2/5. Let me know if we didn't clear that up with the discussion. It's kind of a strange question, so I understand if you kind of went into that like, what are you talking about? But hopefully we've fixed that up. Let me know if you have questions about it. All right, the rest of our day is going to be spent problem solving. A whole bunch of different kind of problems. Jeremy was driving the 120 miles from Mobile, Alabama to New Orleans. His car ran out of gas after he had gone 1/3 of the second half of the trip. How far is Jeremy from New Orleans? It's possible that you might not immediately think length model for this, but gosh, it sure sets up beautifully for it. He's driving from Mobile to New Orleans. So if we just kind of draw that out and go, okay, here's Mobile, here's Mobile, and here's New Orleans, and he's driving. His car ran out of gas after he'd gone 1/3 of the second half of the trip. So if we want to put this on here, I need to sort of chop it up a little bit. So there's half. So, okay, here's the first half of the trip, and this is the second half of the trip. And he had gone 1/3 of the second half. So I need to cut that into thirds, which means when he ran out of gas, he was right here. Let me know if you don't see how I built this picture of this situation. We started out with the whole thing, 1. We chopped it in half, and then we went with 1/3 of that because that's what we were given. He ran out of gas after he had gone 1/3 of the second half. So we need to identify the second half, and then he'd only traveled 1/3 of that. So that's where our picture came from. The question says, how far is he from New Orleans? Well, we know where he is now. And we've chopped this half into thirds. We can also chop the first half into thirds. And now we have equal pieces going all the way across. I have, let's see, how many equal pieces do I have? I have 1, 2, 3, 4, 5. I have 6 equal pieces. And the total is 120 miles. So if I do the 120 miles divided by 6 equal pieces, that means each piece of this is 20 miles. And if each piece is 20 miles, and the question is, how far is Jeremy from New Orleans? Then I can look at this and say, well, if this is 20 miles and this is 20 miles, then Jeremy is 40 miles from New Orleans. One of the things I find super cool about the length, area, and discrete models is we can solve problems without using equations at all. For those of you who never really liked the symbolic manipulation that goes with algebra, this is a way to solve problems without algebra. We just did it. You could do this one with algebra. It'd be kind of an ugly equation to set up, but we don't need to do algebra. We can do it with a picture. And I hope that makes sense. You let me know if it doesn't. I promise I'll be giving you opportunities to solve some of these with polls as we keep going. Okay. The area model, kind of our superpower. A college had to reduce its faculty by 1/6 because of low enrollment. The college now has 350 faculty members. How many faculty members did the college have before the reduction? We've looked at problems with the area model before, so this may be something that you feel like you could solve. And if so, I think that's great. Basically, I want to make sure I'm able to get through all of the examples I want to do with you today. So rather than setting up a poll for this, I'm going to go ahead and go through it. So they had to reduce its faculty by 1/6 because of low enrollment. So first we're going to start out with a picture showing the entire faculty. There's everybody. And they had to reduce the faculty by 1/6. So we need to cut this into 6 equal pieces. There's a few different ways you could do this. Maybe you just want to, well, let's see. If I cut it into half and then I cut each of those into thirds, now I have 6 equal pieces. Let's see, 1, 2, 3, 4, 5, 6. Sure enough, 6 equal pieces. You don't have to cut it that way. If you wanted to, you could cut it into 6 equal pieces by going, well, what if I cut it here and then I cut those into thirds? Then now I have 6 equal pieces. Totally fine. Absolutely fine. I'll stick with my original picture, but you could do it a different way. And what we're told is they had to reduce the faculty by 1/6. So what we're told is that these people, 1/6, they're gone. The college now has 350 faculty members. So although I didn't set up a poll for this, I can ask you this question. So how many faculty members are in each of these remaining slices over here? How many faculty members does each remaining slice represent? Excellent, Courtney. 70. So what we're saying is we have 350 faculty members left, and that's 1, 2, 3, 4, 5 pieces. So there are 5 pieces of this picture that represent 350 faculty members. So if we divide, each piece has 70 faculty members in it. So that means each of these pieces is 70 faculty members. How many faculty members did the college have before the reduction? Well, it had 70 more than it has now. And so you could get there a couple different ways. You could say there's 350 now. If we add those 70 back in, they originally had 420. Or you might say, well, once I know each piece is 70 and there are 6 of them, I could just do 6 times 70 and have 420 total. Either way, how many faculty members did the college have before the reduction? it had 420. Again, using the area model to solve a problem rather than setting up an equation. Questions on that one? I think the problem solving with models are kind of fun. I hope you do too. Now I'm going to give you a chance to try one. In a neighborhood, half of the houses need their shutters painted. Of those, 2/3 have black shutters. If 20 houses have black shutters that need painted, how many houses are there in the neighborhood? I want you to try this with the area model. I'll give you a little time on this. Try to solve this one, and I will put up a poll for it. This will involve drawing a picture. Your one, will be the whole neighborhood. Then you want to chop it up and use the information you were given. This might be a skill that's new, but I think it's a skill that you can master because using the pictures is kind of a cool thing. And I think this is one of those things where once you get it, you get it. It might take a little practice, but we'll keep working on them. I'll give you some time on this. So your picture starts with the whole neighborhood, and then we chop it into pieces. We'll go another 30 seconds on this and then talk about it together. Okay. Not unanimous, but definitely strong agreement here on 60. Let's take a look at it. Okay, so in the neighborhood, half of the houses need their shutters painted. Of those, 2/3 have black shutters. So we'll start out by drawing our neighborhood, or our area model that represents our entire neighborhood. Half of the houses need their shutters painted. So over here are the houses that need their shutters painted. Of those, 2/3 have black shutters. So of those houses, 2/3 have black shutters. So here are our black shutters. If 20 houses have black shutters that need painted, how many houses are there in the neighborhood? So what that means is that these together make up 20 houses. So each piece has 10 houses in it. And then how many houses are in the neighborhood? Well, now we know each of those slices is 10. There's a couple of different ways you could go from here. One way is, well, this would be 10. So there's 30 houses that need their shutters painted. So there's 30 houses that don't. So there's 60 houses altogether. Or you might say, well, if each piece is 10, I'm going to make all the pieces the same size. Then these are all 10 also. And adding those all up together, there are 60. Either way, I hope you're able to draw this picture and solve this problem using the area model. Does anybody have questions they want to ask about that one? Oh, let me back up some of my scribbles here. Okay, so at this point, we're told 20 houses have black shutters that need painted. And so that's these houses right here. Those are the ones that have black shutters that need painted. So there's 20 houses, and that's 2 slices. So we'll take 20 houses that need painted divided by 2 slices, means that each one of these slices must have 10 houses in it. Perfect. Very good. Very good. Okay. Up next, in a city, 4/5 of the men enjoy their jobs and 2/3 of the women enjoy their jobs. What fraction of the population does not enjoy their job? I don't think this is an easy question. I think as area model problems go, I think this is a pretty tough one. So we'll work through this one together. So in this city, we have men and we have women. That's an assumption we're going to make as we solve this. So there's everybody. 4/5 is the men enjoy their jobs and 2/3 of the women enjoy their jobs. It's not told in the problem, but the assumption we're going to make is that half of the people are men and half of the people are women. So we'll cut this right down the middle, and we've got men over here and women over here. So we're making that assumption because that's something that allows us to solve this problem. So 4/5 of the men enjoy their jobs. So if we want to identify them, we'll need to cut this into 5 equal parts. And the ones that enjoy their jobs are these 4/5. Let me know if you see something that is confusing or doesn't make sense. And then 2/3 of the women enjoy their jobs. So we want to cut the women into thirds and say that 2/3 of the women enjoy their jobs. So we've got a picture here that shows half the people are men, half the people are women. 4/5 of the men enjoy their jobs and 2/3 of the women enjoy their jobs. What fraction of the population does not enjoy their job? And so what we're trying to find out here is what fraction of the population is represented by those unshaded pieces. In order to do this, what we want to do is we want to cut this up so that every piece of the picture is the same size. Instinctively, you may not have thought to shade women the opposite direction of the men here, but it's an important thing to do. And the reason is by cutting this both directions, we can make everything the same size. So in a problem like this one, cut them, if you cut the men with horizontal lines, then cut the women with vertical lines. Because what that allows us to do next is, all right, I cut the women's side into thirds. You know what? I'm also going to cut the men's side into thirds. And I cut the men's side into fifths. I'm also going to continue those lines over here to cut the women's side into fifths. Because what I wanted to do here is create equal size pieces all the way through the entire diagram. And now I can see that I have what, 1, 2, 3, 4, 5, 6, 10, 15, 20. I have 25 total pieces in my diagram. Is that right? 1, 2, 3, 4, 5, 6, 12, 18, 24, 30. There we go. 6 times 5, 30 total pieces. So I have 30 total pieces in my diagram. The question said, what fraction of the population does not enjoy their job? Well, out of those 30 pieces, the people that don't enjoy their jobs would be 1, 2, 3, 4, 5, 6, 7, 8. So what fraction does not enjoy their job? 8 out of 30. We could reduce that and say 4/15 of this population does not enjoy their job. I think that's a really challenging question. Hopefully every step we did along the way made sense, and a key there that is important was cutting, if we cut the men horizontally, we cut the women vertically, so that when we cut everything, we've got same size pieces all the way through the diagram. One more topic that we're going to spend the rest of our class time on is remainders. I don't think the remainders topic is really hard. I just want to make sure that you see the difference between what the remainder means if we use the area model versus if we use the standard algorithm. Here's a problem for us to look at. Caitlin has 4 cups of flour, and a recipe calls for 1 2/3 cups per loaf of bread. How many loaves can she make? And how many cups of flour are left over? This is similar to a problem we saw when we first introduced the area model. If I want to know how many loaves she can make, well, she has 4 cups of flour, so I can make my 4 cups of flour. And each recipe calls for 1 2/3 cups. So I need to cut these into thirds. And the way to think of cutting something into thirds when you're drawing these pictures is just think peace sign, because that's cutting it into thirds. Okay. And so how many loaves can she make? Okay, well, loaf number 1 is going to require 1 whole cup plus 2/3 of another cup. That's the first loaf. Loaf number 2 is going to require, well, 1 whole loaf plus 2/3 of another, and that's it. I don't have any more. I'm done. How many loaves can she make? She can make 2 loaves of bread. And how many cups of flour are left over? Well, she doesn't have a whole cup left over. How many cups of flour are left over? By looking at this picture, we can see it. How much flour does she have left? What fraction of a cup does she have left? Excellent, Zochel. Excellent lesson. She has 2/3 of a cup left over. I want to look at this exact same problem, but this time we're going to use the standard algorithm for division. Caitlin has 4 cups of flour. A recipe calls for 1 2/3 cups per loaf. How many loaves can she make? Okay, well, really what we need to do here is she has 4 cups. We want to divide by 1 2/3 to see how many loaves she can make. We've got a mixed number. We want to rewrite that as an improper fraction. So this will be 4 divided by, let's see, 3 times 1 is 3 plus 2 is 5/3. But we're not just going to divide. Division is the same as multiplying by the reciprocal. So this is 4 times 5/3. Or wait, 3/5, I'm sorry. 4 times 3/5. Now we can multiply. 4 over 1 times 3 over 5, that's 12/5. And then we can do 12 divided by 5. And I get 2.4. Well, the decimal part's not important to me here. I want to rewrite that as a mixed number. So we have 2. And then, let's see. That'd be 2 of those 5s would be 10/5. And so I'm left with 2/5 more. So my answer here is 2 2/5. The question was, how many loaves can she make? She can make 2 whole loaves. We better get the same answer we got the other way. And we did. She can make 2 loaves. She can make 2 loaves. What's different and why we're going to focus on this for a little bit here is the remainder. Oops. When we solved it with the area model, the remainder that we got was 2/3. 2/3 of a cup. That was how much flour was left over. When we solved this with the standard algorithm, we got the same answer of 2, but our remainder was 2/5. That's different than the remainder of 2/3 that we got last time. So the remainder's not the same, and it depends on which model you use. When you use the area model, the remainder lets you know how much flour is left over. We can see that from our picture. When you use the standard algorithm, the remainder that you get is not how much flour is left over. This is the number of loaves, that could be made with the remaining flour. So there's a reason that the 2 remainders are different. It's because they mean different things. Here, she has 2/3 of a cup left over. Very straightforward, very easy to see in the picture. This is a little harder to wrap your head around. The key is that it means something different. When you use this approach instead of the area model, your answer is also about the number of loaves, not about the cups of flour that are left over. I want to have you try a problem. Still talking about Caitlin here. She has 3 cups of flour, and a recipe calls for 4/5 of a cup per loaf. When she does this baking, how many cups of flour are left over? And what fraction of a loaf could be made with the remaining flour? What you're really being asked to do here is solve this with the area model, find the remainder, and solve this with the standard algorithm and find the remainder. I'll post a poll for this. We'll have to do it pretty quickly because we're short on time, but the idea here is solve this problem both ways, and once you have, look at your remainder and make sure you know what it means. And the key here, what we're really zeroing in on is, if we solve this one way, we get a remainder that's different than if we solve it the other way. And because of that, it's important to know what those remainders represent. The one thing I will tell you is, because the area model is a picture of the flower, that helps us know which of these things the area model remainder represents. Like I said, we'd probably have to go shorter on this one, maybe shorter than you need it to be, but I want to go ahead and talk about it. So we can go ahead and look at the results of this, but you probably didn't have enough time to do it, and that's just because we had to kind of go, yeah, only a few people were able to finish this one. But let's go ahead and talk about it together. So there are two ways to solve this problem. One way is using the area model, and we're going to do that first. So the first thing we're going to do is look at this with the area model. Caitlin has 3 cups of flour. And a recipe calls for 4/5 of a cup of loaf. You know what? Because it's fifths, I'm not going to use circles, I'm going to use rectangles. Because I don't know if I can cut circles into fifths, but I can cut rectangles into fifths. All right, so I've got them cut into fifths, and recipe calls for 4/5 of a cup per loaf. So there's loaf number 1. 1, 2, 3, 4. 1, 2, 3, 4. That's it. So we can see that she can make 3 loaves. And how many cups of flour are left over? There's 1, 2, 3 out of 5. So 3/5 of a cup is left over. The area model lets us know how many cups are left. We drew pictures of the cups. So we can just see by looking at this, that's 3/5 of a cup of flour. Now the second question says, what fraction of a loaf can be made with the remaining flour? And the way we get that is by solving the problem using the standard algorithm, which will be 3 divided by 4/5. Division is the same as multiplying by the reciprocal. That's 15/4, which we would rewrite as a mixed number. It would be 3, and let's see, 3 times 4 is 12, so that leaves 3/4. So again, we see she can make 3 loaves, and the fraction of a loaf that can be made with the remaining flour, that's what this remainder gives us. She can make 3/4 of a loaf with the flour that she has left. The key here is the remainders we get are different, and they have different meanings. Last thing I want to say before we close today is in number 22, it's okay to use algorithm. And for number 36, trial and error is a perfectly good method. It's fine for you to use trial and error for that one if you want to.